the level curve of f is tangent to the hyperbola. And remember, the hyperbola is given by the equation g equals 3, so it's a level curve of g. Okay, so we have a level curve of f and a level curve of g that are tangent to each other. And I claim that's going to be the general situation that we're interested in. So how do we look for, try to solve for points where this happens? So how do we find xy where the level curves of f and g are tangent to each other? Well, so let's think for a second. If the two level curves are tangent to each other, that means that they have the same tangent line, right? If they have the same tangent line, that means that the normal vectors should be parallel. Okay? Let me maybe draw a picture here. So this is the level curve, maybe f equals something. And this is the level curve g equals constant. Here my constant is 3. Well, if I look at the gradient vectors, so the gradient of f will be perpendicular to the level curve of f. The gradient of g will be perpendicular to the level curve of g. They don't have any reason to be of the same size, okay? But they have to be parallel to each other. Of course, they could also be parallel pointing in opposite directions. But the key point is that when this happens, the gradient of f is parallel to the gradient of g. Well, let's check that. Okay, so here's a point, and I can plot the gradient of f in blue, the gradient of g in yellow. And you see in most of these places, somehow the two gradients are not really parallel. Actually, I shouldn't be looking at random points. I should be looking only on the hyperbola, right? I want points on the hyperbola where the two gradients are parallel. Well, when does that happen? Looks like it will happen here. Okay? So see, when I'm at the minimum, the two gradient vectors are parallel. Okay? It's not really a proof, it's an example, but it seems to be convincing. So far, things work pretty well. Okay, so how do we decide if two vectors are parallel? Well, they're parallel when they're proportional to each other. So you can write one of them as a constant times the other one. And that constant, usually one uses the Greek letter lambda. Okay? I don't know if you've seen it before. It's the Greek letter for the L. And probably, I'm sure that's somebody's idea of paying a tribute to Lagrange, by putting an L in there. Okay. So lambda is just a constant. And we are looking for a scalar, lambda, and points x and y where this holds. So, in fact, what we are doing is we are replacing a min-max problem in two variables with a constraint between them by a set of equations involving, you will see, three variables. So we had min-max with two variables, x and y, but not independent. We had a constraint g of xy equals constant. And that becomes something new. That becomes a system of equations where we have to solve, well, so let's write down what it means for gradient f to be proportional to gradient g. That means that f sub x should be lambda times g sub x, and f sub y should be lambda times g sub y, right? Because the gradient vectors here are f sub x, f sub y, and g sub x, g sub y. If you have a third variable z, then you have also an equation f sub z equals lambda g sub z. Now, let's see. How many unknowns do we have in these equations? Well, there's x, there's y, and there's lambda. So we have 3 unknowns. We have only 2 equations. Something's missing. Well, yeah, I mean, x and y are not actually independent. They're related by the equation g of xy equals c. So we need to add the constraint g equals c. And now we have 3 equations involving 3 variables. Okay, let's see how that works. So here, remember, we have f equals x squared plus y squared, and g equals xy. Okay, so what's f sub x? That's going to be 2x equals lambda times what is g sub x? Y. Okay, so maybe I should write here f sub x equals lambda g sub x, just to remind you. Then we have f sub y equals lambda g sub y. Why does that, so f sub y is 2y equals lambda times g sub y is x. And then our third equation, g equals c, becomes xy equals 3. Okay, so that's what we would have to solve. Okay, any questions at this point? No? Yes?
How do you know the direction of the gradient for the two-dimensional curve?
How do I know the direction of the gradient? Do you mean, how do I know that it's perpendicular to the level curve?
Yeah, how do you know it points in this direction?
Oh, how do I know whether it points in that direction or in the opposite one? Well, that depends. I mean, we've seen actually last time that the gradient is perpendicular to the level and points towards higher values of a function. So it could be, wait, where did I have them? Yeah, it could be that my gradient vectors up there actually point in opposite directions. It doesn't matter to me because it will still look the same in terms of the equation, just lambda will be positive or negative depending on the case. Okay, so I can handle both situations. It's not a problem. So yeah, I can allow lambda to be positive or negative. And well, in this example, it looks like lambda will be positive if you look at the picture on the plot. Yes?
If you're trying to find where the hyperbola and the circles intersect, why can't you just set the two functions equal to each other?
Well, because actually they are not equal to each other. If you look at, so if you look at this point where the hyperbola and the circle touch each other, so first of all, I don't know which circle I'm going to look at.